Let's take a look at an example problem involving springs, energy, and simple harmonic motion. Now these are not as scary as they look. In fact, once you get familiar with working with these are actually pretty straightforward things. There's a few relationships I want to point out, so let's go ahead and get started. A 0.650 gram mass, I'm going to record that, m equals 0.650. Ew, I don't like my pen, I'm going to change that. Alright. Is suspended on a spring, K equals 184 newtons per meter, is pushed from the equilibrium position given an initial velocity of 2.26 meters per second. Now let's think about that for a minute. When you have an oscillator, okay, if this thing's hanging at the equilibrium position, it's given a sharp tap at 2.26 meters per second. That's actually the maximum velocity because as it moves up, gravity slows it down, slows it down, slows it down until it stops. Then it falls back down, speeding up, speeding up, speeding up, speeding up because gravity is pulling harder than the spring until it reaches equilibrium again. And then it continues to move but gets slower, slower, slower. So right there, that velocity, that is the V max. That's its velocity at equilibrium, which is 2.26 meters per second. Finally, nope, that's it. That's all I know. Okay, so let's get started with the problem. A, determine the frequency and period. Well, remember, frequency and period are related by the equation 1 over t, and also frequency is related to omega because we know that the frequency times 2 pi is equal to omega. But that doesn't necessarily help me, except that there is a relationship between omega and k and m. Remember, omega is equal to the square root of k over m, which means I can find omega, and because I can find omega, I can find frequency. So all I have to do here is take the square root of 184 divided by 0.65. So 184 divided by 0.65 raised to the 1/2 power gets me omega, which is 16.82, and this is angular frequency, so this is 16.82 radians per second. And if I divide omega by 2 pi, I get the frequency, so divide by 2 pi in parentheses, so I don't end up dividing by 2 and multiplying by pi. So omega divided by 2 pi equals f, which equals 2.68 hertz. And then if I want t is just 1 over f, so all I have to do is invert that or raise it to the -1 power, and I get t equals 0.373 seconds. So this relationship right here, this omega equals k over m, that is a pretty powerful relationship. You can use it a lot because if you're given frequency, you can find things. If you're given spring constant and mass, you can find others. So remember this, omega equals square root of k over m is a very important, useful tool. B, we're supposed to find the amplitude. Alright, well, this one might be a little bit tricky, except that we know there's a relationship between kinetic energy and amplitude, and we know there's a relationship between position and amplitude. So we know the kinetic energy well, the total energy of the system is equal to 1/2 kx squared plus 1/2 mv squared, where x is any position and v is the velocity at that position. Well, if we're at equilibrium, then all the energy is kinetic energy, and so there is no elastic potential or gravitational potential energy. They go away. So the kinetic energy is equal to 1/2 mv max squared. But at its highest point, or its lowest point, the potential energy is the energy, and that's equal to 1/2 ka squared. So we know 1/2 ka squared equals 1/2 mv max squared, and so there's a half on both sides, so they go away. So if I want a, all I have to do is divide by k and square root. So a equals m divided by k times v max squared, and that whole thing is square rooted. So I know m, it's 0.65. We know k, divided by 184. And we know v max, it was given, so times 2.26 squared and raise that to the 1/2 power, and we get an amplitude A equals 0.134 meters, or 13.4 centimeters. Finally, nope, not finally, we're just still moving on. C says give its position as a function of time. Well, since it started right here at the middle, we know that it started at equilibrium and went up, so we don't have to worry about a phase angle. So we can just say y equals a sine omega t. Well, we know all these things. We know y is the position as a function of time. A, we just found, is 13.4. Sine omega, I guess I found omega right there. If I wanted to, I could rewrite it as that. I probably will, because it's more precise to write it as the square root of 184 over 0.65 times t. So there's the position as a function of time. And then D, the total energy. Well, like we said before, total energy is the kinetic energy when the velocity is a maximum, or the potential energy when the amplitude is a maximum. So this is just equal to the kinetic energy at max, which is 1/2 mv max squared, which is 1/2 of 0.65 times 2.26 squared. 0.5 times 0.65 times 2.26 squared is 1.66 joules. Finally, E, kinetic energy at 0.4a. Now that is a little bit tricky. E, Ke at 0.4a. There's a couple different ways I can go about doing this. I know that the total energy is equal to kinetic energy plus potential energy. That is to say, this is equal to 1/2 mv squared plus 1/2 kx squared. Now I want the kinetic energy at 0.4a. So I can either find the potential energy there, subtract it from the total energy, divide by mass, double it, and square root it, and get v. Or I can go through and I can say, well, velocity is equal to the square root of k over m times a squared minus x squared. Now this equation is not magical, it's just a derivation from right here, because this equation is equal to this equation is equal to this equation. If I just want to solve this equation for v, then I'm going to say, well, 1/2 kx squared plus 1/2 mv squared equals 1/2, and I guess I'm going to use this one, ka squared. So if I solve this for v, I have 1/2 mv squared equals 1/2 ka squared minus 1/2 kx squared. Now there's a 1/2 in every single one of those, so I can divide it out, cross it off, and so now I have mv squared equals that's gone, k, and this is in both, so I'm going to factor it out, k times a squared minus x squared, divide both sides by m, so I get v squared equals k over m times a squared minus x squared, and then I can square root both sides. V equals the square root of k over m times a squared minus x squared. So I can use this equation as well to find out the velocity and get the kinetic energy. So it depends on what you want to do. I guess I'll just derive this, so I'll use it. So the velocity is equal to the square root of k, which I know to be 184 over m, which is 0.65, right? Got to double check that. 0.65 times a squared, and a we calculated up above to be 0.134 squared minus x squared. Well, at 0.4a, so this is times 0.4, 0.134, and this whole quantity gets squared, and that'll give me its velocity. So 0.134 squared minus 0.4 times 0.134 squared, and then multiply that by 184, divide it by 0.65, raise it to the 1/2 power, and I get a velocity v equals 2.066 meters per second. I can go ahead and run that into the kinetic energy equation. Ke equals 1/2 mv squared, so 0.5 times 0.65 times that 2.066 squared gets me 1.38 joules. Now I can double check that answer, because if I find the potential energy at point 4A, which I can do, potential energy equals 1/2 kx squared. So at point 4A, this is 1/2 times 184 times 0.4 times 0.4, times 0.134 quantity squared. So I have 0.5 times 184 times 0.4 times 0.134 quantity squared equals 0.264. If I subtract that number from the total energy, which we found right here, we should come up with this 1.38. So 1.66 minus that energy we just calculated does in fact equal 1.39. So give or take a rounding error, these two agree with each other. So there's the potential energy. So if I take the energy minus the potential energy, I do get the kinetic energy. So it all works out. You can do that problem from a variety of different ways.